Thank you for watching my presentation on the distribution of planets. I'm Stuart Taylor, and I'm going to be talking about some major features in the distribution of planets that basically define the distribution of a major population of planets. The population of planets being, I'm going to refer to objects of sun-like stars. And by sun-like stars, I mean stars excluding planets of binary stars. And then also, last year I said excluding planets of stars with low surface gravity. So only planets of stars with surface gravity of above 4. And then I'm further subdividing these sun-like stars into planets of iron-rich stars, metallicity as high or higher than our sun, and metal-poor stars, stars with poor metallicity. And what I published last year in Astronomy that in this metal-rich population, subpopulation, found a peak-gap peak feature, a very sharp gap, where there were no planets adjacent to a very high peak. And so that's what we have here in red, have all 429 objects that were found by radial velocity here. In black, in green, we have the other ones. So the red plus green equals the black. This year, rather than plot by period, learned that if plot the stellar mass versus semi-major axis, that there's a dependence on the mass of the star, such that a dependence of the stellar mass squared. So this is pretty much the same population of iron-rich stars, sun-like stars, except now for sun-like, I'm including all the stars of all surface gravity, where you can, I'll call the sun-like stars those stars that basically that have substantial convective zone, that have stellar masses less than 1.29 solar masses. Now, this is also including the iron-poor objects and the binary star objects, iron-poor and unfilled circles, binary star and squares, and you can see why you usually don't quite see the features. They're kind of there, you can kind of see them, but the iron-poor stars, binary star objects, they don't follow this. Interestingly, so this is the shallow gap, and then this is the deep gap. This little cluster, interestingly, it appears to fall on the 3:2 resonance, and out here is where the 1:2 resonance is. So I binned these objects this time in slanting bins with the dependence on the stellar mass, the square root of the stellar mass, multiply it by the square root of the stellar mass, take out the stellar mass squared dependence, and you can see the peak gap peak feature here quite clearly, which appears to me to show that planets probably form with an inner and outer disk, with the outer disk typically in the same location. And planets can migrate out from the gap, they can migrate in, but they don't really migrate into the gap and stop. They might migrate quickly and rarely stop. These features also have an influence on the eccentricity, where here I've plotted the sun-like stars, planets that are sun-like objects, the orbital period and the eccentricity, and then the red open circles are the iron-rich objects, and the blue filled circles are the iron-poor objects, or planets of stars with metallicity less than our sun. And this shows, as we found in 2012-13, looking at the mean eccentricity for here of metal poor stars, here metal rich stars, you see that metal rich stars, the mean eccentricity is pretty much higher at shortest periods, as found earlier, and also longer periods appears to reappear. But the eccentricities of metal poor stars seems to have a peak around where the density of planets per log period is highest, and this also corresponds to the gap. So the structure appears to have a relationship with the eccentricity. So I hope you contact me to talk about these features. I'm Stuart Taylor in Hong Kong. I brand myself Participation World Scope, and I hope that you please contact me. Thank you.